from the Lawrence Hall of Science. Now, we've been doing these Astrophysics Friday videos for a while now, and it makes me think about how fast time flies. Our first video was uploaded 4 months ago, and 4 months is one third of a year.
And since a year is the amount of time it takes for the Earth to make one full orbit around the Sun, this means the Earth has traveled one third of its orbital period since Astrophysics Friday was born. Wow!
But wait, how do we know how long it takes for the Earth to go around the Sun in the first place? Or how long it takes for other planets to go around the Sun? To answer this question, let's consult the astronomer Johannes Kepler.
In the 17th century, Kepler published three laws describing the motions of the planets around the Sun. Kepler could only study the planets of our solar system. But today, we know that his laws apply to planets orbiting around other stars as well, which you may know are called exoplanets. The first of these laws just states that the orbit of a planet is an ellipse. As we've mentioned before in this series, an ellipse is a circle that's been stretched out. The more an ellipse is stretched out, the higher its ellipticity is. An ellipse has two foci, and the star a planet is orbiting around is at one of these 2 points. In our last video about dark matter, we mentioned Kepler's second law, which says that a light segment joining a planet and the Sun sweeps out equal areas in equal times. This means that a planet travels fastest when it is at its closest approach to its host star, and the planet travels slowest when it is at the point in its orbit farthest from its host star. Now, let's discuss Kepler's third law, which states that the square of a planet's orbital period is proportional to the cube of the length of the semi-major axis of its orbit. That might sound kind of confusing, but there's a handy equation representing this law that we can break down. In this equation, T is the period of a planet. The period of a planet is just how long it takes to make one complete orbit around its host star. M is the mass of the host star, and R is the semi-major axis of the planet's orbit. Remember from Kepler's first law that the orbit of a planet is an ellipse. The semi-major axis of an ellipse is the distance from the center of the ellipse to one of the two farthest points of the ellipse from the center. Looking at this equation, what do you think happens to T if we make R bigger? If you said T gets bigger, you are right. This means that the farther away a planet is from its star, the longer its period is, or the longer it takes to make a full orbit. Let's take a look at how well this equation holds true for our solar system. If we plug in the mass of the Sun for M and the semi-major axis of Earth's orbit for R, putting all of these numbers into a calculator will give us the period of the Earth.
You can try calculating the periods of other solar system planets yourself. Let's practice together. Grab a pen, a paper, and a calculator near you. If you don't have a physical calculator, you can use an online one, like the one we've linked for you down below. You can pause the video while you grab everything. I'll wait. Oh, you're back. Are you ready? Great! Now, our mission is to calculate the period of Mars. And don't worry, astronomers in training, I'll guide you along the way. A good first step for most astrophysics problems is to write down the equation you'll be using. So go ahead and write down t squared equals, open bracket, 4 pi squared over gm, close bracket, times r cubed.
Now, I'm going to give you some numbers, so make sure to take note of them. Roughly, the semi-major axis of Mars's orbit is about 230 million kilometers. That's 6 zeros after 230. But we actually want to use meters in this equation. So we must multiply this value by the number of meters in 1 kilometer, which is 1,000. Now, you should have that the semi-major axis of Mars's orbit is 230 billion meters. That's 9 zeros after 230. We're using the same values for the mass of the Sun and the gravitational constant as we saw before. M is about 1.99 times 10 to the power of 30 kilograms, and G is about 6.67 times 10 to the power of minus 11 newtons times square meters over square kilograms. Don't worry if some of these units like newtons and square kilograms are unfamiliar to you. Just know that in the end, our answer will be in units of seconds.
So you have the numbers. What should you do now? Right, you have to plug them in. Replace G with the gravitational constant, M with the mass of the Sun, and R with Mars's distance from the Sun. Now just plug in the numbers into your calculator. What number do you get?
You should get a huge value because this answer is in seconds. There are 86 and 400 seconds in a day. So if we divide our answer in seconds by the number of seconds in a day, we get an answer in a number of days. It turns out that Mars's period is 687 days, which is almost twice the time it takes for the Earth to go around the Sun.
Did you get it right? If you did, great job! If you didn't, don't worry. You have plenty of time to practice. You are, after all, an astronomer in training. Try calculating the periods of other planets too. There's a link in the description with all the planets' semi-major axes values. And to check your answer, you can see the link titled Solar System Planets Periods. Well, that's all from us today. Thank you so much for watching. Don't forget to give this video a like and subscribe to our channel for more science content. I will see you later and keep asking big questions about the universe. Bye!